ओके, सो सबसे पहले एटॉमिक मासेस फॉर एन इनसाइट, ये सब चीज तुम लोग जूनियर क्लासेस में पढ़ चुके हो या फिर केमिस्ट्री में पढ़ चुके हो, तो मैं थोड़ा तेजी से ही निकालूंगा। तुम लोग को जहां पे पूछना होगा वहां पे रोक के पूछ लेना मेरे से। So atomic masses, for an insight into the nuclear phenomena, it is essential to determine accurately the atomic masses of an element. The instrument designed for this purpose is called a mass spectrometer. The unit in which atomic and nuclear masses are measured is called atomic mass unit. AMU उसका short form है, Unified Mass Unit. ठीक है, AMU कहते हैं या फिर U से रिप्रेजेंट करते हैं, तो आजकल जनरली U से ही तुम देखोगे रिप्रेजेंटेशन। One atomic mass unit or unified mass unit is defined as 1 by 12th of the mass of the atom of carbon C612 isotope. Now, as Avogadro's number is equal to 6.023 into 10 to the power 23, mass of 6.023 into 10 to the power 23 atoms of carbon 12 element, इतने सारे एक एवोगैड्रो नंबर के इतने एटम्स के जो मास है दैट इज इक्वल टू एटॉमिक मास 12 ग्राम्स। सो मास ऑफ वन एटम ऑफ कार्बन 12 विल बी 12 डिवाइडेड बाय इतना, है ना। तो बाय डेफिनेशन 1 AMU is 1 by 12 the mass of an atom of carbon. So 1 by 12th the mass of 12 by 6.023 into 10 to the power 23 करोगे 1.66 into 10 to the power minus 24 ग्राम्स आता है। केजी में करोगे तो 1.66 into 10 to the power minus 27 kg आएगा। तो ये हमारा एक रिलेशन हो गया 1 AMU और ग्राम के बीच में। नाउ as an atom of C612 contains 12 nucleons, ठीक है, 12 प्रोटॉन है 12 न्यूट्रॉन है, ठीक है, सॉरी 6 प्रोटॉन है 6 न्यूट्रॉन है, टोटल 12 न्यूक्लियॉन्स हो गए। जितने न्यूक्लियस में जो पार्टिकल्स हैं उन सबको न्यूक्लियॉन कहते हैं। सो देयरफॉर 1 AMU रिप्रेजेंट्स द एवरेज मास ऑफ ए न्यूक्लियॉन एंड is denoted by U. In terms of this unit, mass of an electron is 0.00055 U, ठीक है, and mass of proton is equal to 1.0073 U. Mass of a hydrogen atom is, हाइड्रोजन में एक इलेक्ट्रॉन और एक प्रोटॉन होगा, 1.0078 U. Mass of a neutron is 1.0086 U. Now, 1 electron volt is the energy gained by an electron when accelerated through a potential difference of 1 volt. So, as work done is equal to charge into potential, hence 1 electron volt is equal to 1.602 10 to the power minus 19 coulomb or 1.602 10 to the power minus 19 joule. 1 mega electron volt is 10 to the power 6 electron volt, 1.602 10 to the power minus 13 joule. Relation between AMU and MEV के बीच में according to Einstein mass energy equivalence is represented by E is equal to mc square. अब हम लोग m is equal to 1 AMU अगर पुट करें, ठीक है, m is equal to 1 AMU which is 1.66 10 to the power minus 27 kg and C is 3 into 10 to the power 8 meter per second. So we get E as 1.66 10 to the power minus 27, 3 into 10 to the power 8 का whole square, तो ये 1.49 10 to the power minus 10 जूल होता है। सो इसको अगर हम लोग मेगा इलेक्ट्रॉन वोल्ट में कन्वर्ट करेंगे, सो 1.49 10 to the power minus 10 by 1.6 10 to the power minus 13 से डिवाइड कर देंगे, राइट, ये जो आया था MEV का, तो 931.25 MEV आता है। सो ये रिलेशन, ये जो डेरिवेशन है ना 1 AMU का MEV में, ये कभी कभी आता है, ठीक है, तो ये वाला पोर्शन बस कर लेना, रिलेशन बिटवीन AMU एंड MEV। तो 1 AMU इज इक्वल टू 931 MEV, विच इज यूज्ड एज अ स्टैंडर्ड कन्वर्जन। तो ये हम लोग काफी न्यूमेरिकल्स में यूज करेंगे। जब एएमयू में आ जाएगा और हमको एमईवी में लिखना होगा मेगा इलेक्ट्रॉन वोल्ट में, तो उसको हम लोग डायरेक्टली 931 से मल्टीप्लाई करके निकाल लेते हैं ना। Composition of nucleus. So, the study of radioactive disintegrations indicates the emission of alpha, beta, and gamma particles or rays to be of nuclear origin. Further, study of artificial radioactivity has revealed that many other particles like proton, neutron, alpha particle, beta particles, and subparticles like meson, positron, and neutrino enter into the constitution of the nucleus in one way or the other. Based on these studies, several hypotheses have been put forward about the structure of the atomic nucleus. Prominent among them are proton electron hypothesis and proton neutron hypothesis. तो दो थ्योरी है जिसको कि जो काफी पूछा जाता है कि प्रोटॉन इलेक्ट्रॉन हाइपोथेसिस के हिसाब से समझाना या प्रोटॉन न्यूट्रॉन हाइपोथेसिस को एक्सप्लेन करना. So this was put forward in the year 1930, proton electron hypothesis, to account for the emission of alpha and beta particle from the nucleus of radioactive elements. The positive charge in the nucleus is that of protons. A proton carries 1 unit of fundamental positive charge and is stable. An electron carries 1 unit of fundamental negative charge and its mass is negligible compared to mass of proton. Now, according to proton electron hypothesis, the nucleus of an atom of mass number A and atomic number Z is made by A protons, और electrons कितने हो जाएंगे? Basically A proton और A minus Z न्यूट्रॉन होगा अगर हम न्यूक्लियस के बारे में बात करते हैं. ठीक है. अच्छा सॉरी, ये प्रोटॉन इलेक्ट्रॉन हाइपोथेसिस है ना, यही ये इन्होंने गलत ये किया था. सो एज एवरी एटम इज इलेक्ट्रिकली न्यूट्रल इट मस्ट कंटेन Z मोर इलेक्ट्रॉन्स, है ना. यहाँ पे A माइनस Z इलेक्ट्रॉन्स कह रहे हैं, राइट. तो Z मोर इलेक्ट्रॉन्स they revolve around the nucleus in circular orbits. However, this hypothesis was rejected later, ठीक है, क्योंकि ये wrong था hypothesis. अब उसके बाद आया डिस्कवरी ऑफ न्यूट्रॉन, है ना. अ न्यूट्रॉन इज अ न्यूट्रल पार्टिकल, ठीक है. सो अ न्यूट्रॉन इज अ न्यूट्रल पार्टिकल कैरिंग नो चार्ज एंड हैविंग मास equal roughly to the mass of a proton. This particle was discovered experimentally by Chadwick in year 1932. Chadwick estimated the mass of neutron being roughly equal to mass of proton. Whereas a free proton is stable, a free neutron is unstable and has a mean life of 1000 seconds. Neutron is, however, stable inside the nucleus. Now, proton-neutron hypothesis. The hypothesis was put forward by Heisenberg after the discovery of neutron by Chadwick. According to this hypothesis, a nucleus of mass number A and atomic number Z contains Z proton and A minus Z neutron. As an atom is electrically neutral, therefore number of peripheral electrons must be equal to Z, number of proton inside the nucleus. Now, this hypothesis accounted for all the discrepancies of proton-electron hypothesis. Atomic number of an element is the number of protons present inside the nucleus of an atom of the element. It is also equal to number of electrons revolving in various orbits around the nucleus of the atom. It is represented by Z. Now, mass number of an element is the total number of proton and neutron present inside the atomic nucleus of the element. It is represented by A. Thus, in an atom, number of proton is represented by Z, number of electron भी Z ही होगा अगर electrically neutral है, तो number of nucleons A हो जाएगा, number of neutron A minus Z हो जाएगा. A nuclide is a specific nucleus of an atom which is characterized by its atomic number Z and mass number A. It is also called nuclear species. It is represented by XAZ, where X is the chemical symbol of the species. For example, a gold nucleus is represented by AU 19779. ठीक है. It contains 79 protons and 197 minus 79, that is 118 neutrons. ठीक है. Now nuclear size, experimental measurements show that volume of a nucleus is proportional to its mass number A. If R is the radius of the nucleus assumed to be spherical, then its volume is equal to 4 by 3 pi r cube is proportional to A. So R is proportional to A 1 by 3, or R is equal to R naught A 1 by 3, where R naught is an empirical constant whose value is found to be 11.2 into 10 to the power minus 15, 1.2 over 1.2 into 10 to the power minus 15 meter. As A is different for different elements, therefore atomic nucleus of different elements have different sizes. Now nuclear density, nuclear size से nuclear density आएगा. Density of nuclear matter is the ratio of mass of nucleus and its volume. If m is the average mass of a nucleon and r is the nuclear radius, then mass of nucleus is m into a, है ना. एवरेज मास ऑफ ए न्यूक्लियन इंटू जितने न्यूक्लियन है, मास नंबर जितना होगा उतने न्यूक्लियन है, तो m इंटू ए उसका पूरा मास हो जाएगा, वेयर a इज द मास नंबर ऑफ द एलिमेंट. Now volume of nucleus is 4 by 3 pi r cube. उसको r naught a 1 by 3 raised to the power 3 कर देंगे तो 4 by 3 pi r naught cube into a हो गया. Now mass of nucleus by volume of nucleus करेंगे, a कैंसिल हो जाएगा, m 3m by 4 pi r naught cube, ये हमारा density हो गया. ठीक है, nuclear density. As m and r naught are constant यहाँ पे, therefore density rho of nuclear matter is the same for all nuclei. ठीक है. So यहाँ पे देखिए, m का वैल्यू 1.66 इंटू 10 टू द पावर माइनस 27 kg है, r नॉट का वैल्यू 1.2 इंटू 10 टू द पावर माइनस 15 था, है ना, जैसा कि हम लोगों ने यहाँ पे देखा था. अब ये दोनों वैल्यूज इसमें पुट कर देते हैं, तो डेंसिटी क्या हो गया, 3 इंटू एम बाय 4 पाई आर नॉट क्यूब. ये वैल्यू पुट करेंगे तो 2.29 इंटू 10 टू द पावर 17 kg पर मीटर क्यूब आता है. ठीक है, दिस इज द डेंसिटी. सो न्यूक्लियर डेंसिटी इज कांस्टेंट, which is a very large as compared to density of ordinary matter. For example, water का density is 10 to the power 3 kg per meter cube. Air का जो है 1.23 kg per meter cube. Hence matter in the nucleus is very densely packed. अब आते हैं isotopes पे. So isotope of an element are the atoms of the element which have the same atomic number Z but different mass number A. For example, 1H1 है ना, 1H2, 1H3 are the isotopes of hydrogen. He32, He42 और He62 are the isotopes of helium. ठीक है. And so as isotope of an element have the same atomic number, they contain same number of proton and same number of electron, but as their atomic weights are different, they contain different number of neutrons. Isotopes of an element have identical chemical properties, क्योंकि number of proton same होगा तो और इलेक्ट्रॉन सेम है, तो इलेक्ट्रॉनिक कन्फिगरेशन जब किसी एलिमेंट का सेम होता है, कोई भी दो मैटर का, तो इलेक्ट्रॉनिक कन्फिगरेशन सेम होगा तो उसका केमिकल प्रॉपर्टी ऑलमोस्ट सिमिलर होगा. Their physical properties, however, differ. All the known elements have one or more isotopes. The relative abundance of different isotopes differ from element to element. The atomic weight of an element is the weighted average of the masses of all its isotopes based on the occurrence of each isotope in nature. For example, neon has two isotopes of masses 20 and 10 to 22, which occur in the ratio 9:1. Average atomic weight of neon is, तो अगर बिकॉज इसका जो अवेलेबिलिटी है 9:1 है अकरेंस का रेशियो, तो 20 इंटू 9 प्लस 20 एवरेज हम लोग निकालते हैं, वेटेड एवरेज जैसे निकाला जाता है. 9 जिसका है पार्ट, उसका जो वेट होगा उससे मल्टीप्लाई करेंगे 20 इंटू 9, उसके बाद 1 इंटू 22 बाई 9 प्लस 1. तो इससे हम लोग को जो Average weight आता है 20.2. On the contrary, mass number A is always an integer as it represents the number of nucleons in the nucleus. अब आते हैं isobars पे. Isobars are the atoms of different element which have the same mass number but different atomic number. तो यहाँ पे mass number same होगा but atomic number different होगा. ठीक है. Isobars contain different number of protons, different number of electrons, also different number of neutrons. So for example, sodium 2211 और neon 2210, यहाँ mass number same है, atomic number अलग अलग है, are isobars. Similarly, calcium 4020 and argon 4018 are isobars. Bars, chlorines 3717 and sulfur 3716 are also isobars. The chemical properties of isobars are different, are widely different. Their physical properties may be identical. The isobars occupy different places in the periodic table क्योंकि उनका atomic number अलग है, अलग अलग element है, इसीलिए different places in the periodic table. Isotone are the nuclides which contain the same number of neutrons. That is, in their case, A minus Z N is same. Their atomic number Z and mass number A are different. For example, chlorine 3717 and potassium 3919, इन दोनों में देखोगे आर आइसोटोन, नंबर ऑफ न्यूट्रॉन दोनों में 20 है. दिस इज बिकॉज नंबर ऑफ न्यूट्रॉन इन क्लोरीन इज 37 minus 17 20 and number of neutron in potassium is 39 minus 19 which is equal to 20. So similarly, hydrogen 3 1 and helium 4 2 are again isotones. Now mass energy relation, Einstein was the first to establish the equivalence of mass and energy through the famous relation E is equal to mc square, where c is the speed of light in vacuum. The relation means that when a certain mass m disappears, an equivalent amount of energy E appears and vice versa. The mass of a particle measured in a frame of reference in which the particle is at rest is called its rest mass, usually denoted by m naught. The rest mass energy m naught c square, which is enormously large on account of large value of c. If T is the kinetic energy of the particle, then its total energy E is equal to mc square, that is rest mass energy, plus kinetic energy is the total energy. Here m is called the effective mass of the particle when it is moving. Clearly m is greater than m naught. So from equation 3 we have the kinetic energy T is mc square minus m naught c square, or m minus m naught c square, or T is equal to delta mc square. So thus kinetic energy of a particle is change in mass of a particle into speed of light in vacuum ka square. Therefore, the two classical laws of conservation of mass and conservation of energy have been unified into one law. पहले अलग अलग हम लोगों ने पढ़ा था, कंजर्वेशन ऑफ मास और कंजर्वेशन ऑफ एनर्जी. अब उन दोनों को कंबाइन करके एक लॉ बना दिया गया जिसको कहते हैं द लॉ ऑफ कंजर्वेशन ऑफ मास एनर्जी, क्योंकि मास और एनर्जी आपस में कन्वर्ट कर सकते हैं एक दूसरे के फॉर्म में. सो अकॉर्डिंग टू दिस लॉ, the sum of the mass energy of a system of particle is the same before and after an interaction. Now nuclear binding energy, so concept of binding energy of a nucleus is the energy with which nucleons are bound in the nucleus. It is measured by the work required to be done to separate the nucleons an infinite distance apart from the nucleus so that they may not interact with each other. This difference between the sum of masses of neutron and proton forming a nucleus and mass of the nucleus is called mass defect. Now it is mass defect which appears in the form of binding energy responsible for binding the nucleons together in the nucleus. Now expression for nuclear binding energy. So in a nucleus, which is represented as XAZ, Z is the charge number, that is number of proton. A is mass number of proton plus the number of neutron. Number of neutron is A minus Z. MP अगर mass of proton है, Mn mass of neutron है, और M capital N mass of nucleus, ठीक है. So X से Z. So mass defect अगर हम लोग को निकालना हो तो mass defect is delta M, which is equal to नंबर, जो मास ऑफ प्रोटॉन है उसको उसके एटॉमिक नंबर से मल्टीप्लाई कर लिया, मास ऑफ न्यूट्रॉन को उसको नंबर ऑफ न्यूट्रॉन से मल्टीप्लाई कर दिया, माइनस ऑफ mass of the whole nucleus will give you the mass defect delta M, right? So using Einstein's mass energy equivalence, binding energy will be equal to delta mc square, right? सो ये जो डेल्टा एम हम लोगों ने निकाला है उसको हम लोग सी स्क्वायर से मल्टीप्लाई कर लेंगे तो बाइंडिंग एनर्जी के बराबर होगा वो. इफ एम इज द मास ऑफ द एटम, दैट इज एक्स से जेड एक एटम है कंटेनिंग जेड इलेक्ट्रॉन्स, ईच ऑफ मास एम ई, देन वी कैन राइट द मास एम ऑफ एक्स से जेड, है ना, पूरे पूरे एटम का जो मास है इज इक्वल टू मास ऑफ the nucleus plus mass of the electron, Z into mass of electron, minus binding energy of electron by C square. This will give you the mass of the whole atom. So for hydrogen atom of mass mh containing one electron, we can write mh is equal to mp plus me minus binding energy of electron divided by C square. Now the binding energy of electron is much smaller in given in terms of electron volt to kilo electron volt as compared to rest mass energy of a nucleon, that is 10 to the power 3, approximately 10 to the power 3 MeV, mega electron volt. Therefore we can safely ignore in 5 and 6 the term involving binding energy of electron. ठीक है. So equation in 5 and 6 reduces to, तो बाइंडिंग एनर्जी ऑफ इलेक्ट्रॉन जो है ना इसको हम लोग नेग्लेक्ट कर लेते हैं. तो अब हमारा जो मास ऑफ हाइड्रोजन है मास ऑफ प्रोटॉन प्लस मास ऑफ इलेक्ट्रॉन लिखा जा सकता है, और मास ऑफ जो एटम था दैट इज इक्वल टू मास ऑफ न्यूक्लियस प्लस जेड इनटू मास ऑफ इलेक्ट्रॉन. नाउ रीराइटिंग द इक्वेशन 4, है ना, तो इक्वेशन 4 जो हमारा था ये बाइंडिंग एनर्जी वाज इक्वल टू ZMP by A minus ZMN and minus mass of nucleus. तो इसको अगर हम लोग पुट करते हैं, ठीक है, so rewriting equation 4 we get binding energy is equal to atomic number into mass of proton, number of electrons into mass of electron, number of neutron into mass of neutron, minus mass of the nucleus माइनस जेड टाइम्स मास ऑफ इलेक्ट्रॉन. तो ये हम लोग मास ऑफ इलेक्ट्रॉन पहले नहीं कंसिडर कर रहे थे, अब वो भी कंसिडर करेंगे, बाकी सब चीज सेम है. सो using 7 and 8 we get mass of binding energy is equal to mass of proton plus mass of electron. हमारा mass of hydrogen है तो Z into mass of hydrogen plus A minus Z into mass of neutron, mass of neutron, minus M into mass of each this atom into C square. Now average binding energy per nucleon, तो ये एक्सप्रेशन फॉर न्यूक्लियर बाइंडिंग एनर्जी हो गया हमारा. नाउ एवरेज बाइंडिंग एनर्जी पर न्यूक्लियन ऑफ ए न्यूक्लियस, so it is the average energy we have to spend to remove a nucleon from the nucleus to infinite distance. It is given by total binding energy divided by mass number of the nucleus. So the variation of average binding energy per nucleon with mass number A is shown in the figure. ठीक है, तो ये नीचे अभी हम लोग एक फिगर देखेंगे जहाँ पे कि यू विल सी, ये फिगर भी ना समझाना ये आता है क्वेश्चंस में, तो ये वाला पार्ट आप देख लेना, एवरेज बाइंडिंग एनर्जी पर न्यूक्लियन ऑफ न्यूक्लियस, है ना. ये जो इंपॉर्टेंस ऑफ बाइंडिंग एनर्जी कर दिया है, दिस इज ऑल्सो इम्पोर्टेंट. So the variation of average, so it is the, so average binding energy per nucleon of nucleus. So it is average energy we have to spend to remove a nucleon from the nucleus to infinite distance. It is given by total binding energy divided by the mass number of the nucleus. The variation of average binding energy per nucleon with mass number A is shown in the figure. Average binding energy per nucleon for light nuclei like hydrogen 1, hydrogen 2, and hydrogen 3 is small. For mass number ranging from 2 to 20, there are sharply defined peaks corresponding to helium 4, 2, and carbon 12, 6, etc. The peaks indicate that these nuclei are relatively more stable than the other nuclei in their neighborhood. Excuse me. The binding energy curve has a broad maximum. So binding energy curve has a broad maximum in the range A is equal to 30 to A is equal to 120, corresponding to average binding energy per nucleon 3.5 MeV. The peak value of the maximum is 8.8 MeV for Fe5626. As the mass number increases, the binding energy per nucleon decreases, gradually falling to about 7.6 mega electron volt per nucleon for uranium 238-92. The decrease be due to Coulomb repulsion between the protons. The heavy nuclei are therefore relatively less stable. Now, importance of binding energy curve. So when we move from a heavy nuclei region to the middle region of the plot, we find that there will be a gain in the overall binding energy and hence release of energy. This indicates that energy can be released when a heavy nucleus, which is A is equal to 240, breaks into two roughly equal fragments. This process is called nuclear fission. Similarly, when we move from lighter nuclei to heavy nuclei, we again find that there will be gain in the overall binding energy and hence release of energy. This indicates that energy can be released when two or more uh, lighter nuclei fuse together to form a heavy nucleus. This process is called nuclear fusion. Now, packing fraction of a nucleus is defined as the mass excess per nucleon. So, mass excess is the difference between the mass of a nucleus and mass number of the nucleus. So packing fraction is mass excess, the total mass minus of A, m minus A divided by A. So mass excess is different between mass of a nucleus and mass number of the nucleus, where m is the actual height of a nuclide, of actual weight. So where m is the actual weight of the nuclide. Take minute. So sorry. So where m is the actual weight of a nuclide on the physical atomic weight scale, and a is the mass number, while a is the whole number, m is not necessarily so. The variation of packing fraction with mass number a is shown in the figure. सो जैसे जैसे मास नंबर इंक्रीज करेगा, आप देखोगे पैकिंग फ्रैक्शन पहले डिक्रीज करता है और बाद में इंक्रीज करता है. So variation of packing fraction with mass number A is shown in figure. In fact, packing fraction measures the stability of a nucleus. Smaller the packing fraction, larger is the stability of the nucleus. So from the graph, we find that for A is equal to 16, packing fraction is 0. तो यहाँ पे देखो A is equal to 16 पे packing fraction 0 है, right? So for A is equal to 16, packing fraction is 0. For very light nuclei, that is A less than 16, packing fraction is large, therefore they are unstable. तो जब बहुत light nucleus भी होगा तब भी unstable है. As A increases beyond A is equal to 16, packing fraction becomes negative, decreases with increased mass number. Beyond certain value of mass number, packing fraction starts increasing till it becomes 0. At about A greater than 240, packing fraction becomes large, thus heavy nuclei are again unstable. So extremely light nuclei is also stable. A is equal to 16 से ये देखिए, ये पैकिंग फ्रैक्शन जहाँ A greater than 240 तक ये नेगेटिव है, तो इन सब में बेसिकली आपका स्टेबल रहेगा. न्यूक्लियर फोर्सेस, now nuclear forces are the strong forces of attraction which hold together the nucleons, that is neutrons and protons, in the tiny nucleus of an atom. In spite of strong electrostatic forces of repulsion between them. Now, these forces are very complex in nature. Some of the important characteristics of these forces are: पहला है, nuclear forces act between a pair of neutrons, a pair of protons, and also between a neutron proton pair with the same strength. This shows that nuclear forces are independent of charge. तो दो न्यूट्रॉन के बीच में, दो प्रोटॉन के बीच में, और एक न्यूट्रॉन और एक प्रोटॉन के बीच में, हर जगह पे ये न्यूक्लियर फोर्सेस होता है. और इसीलिए ये मतलब इससे ये पता चलता है, और सब में सेम स्ट्रेंथ है, इससे ये पता चलता है कि चार्ज पे डिपेंडेंट नहीं है. न्यूक्लियर फोर्सेस आर द स्ट्रॉन्गेस्ट फोर्सेस इन नेचर. The magnitude of nuclear forces is 100 times that of electrostatic forces and 10 to the power 38 times, ठीक है, 10 to the power 38 times that of gravitational forces between nucleons. That is why nucleons are held together in a nucleus in spite of electrostatic force of repulsion between protons. The nuclear forces are very short range forces. They are operative up to distances of the order of few Fermi. That is, they operate only within the nucleus. The variation of nuclear forces with the distance between nucleon is also known exactly. Is not known exactly, sorry. The variation of nuclear forces with the distance between nucleons is not known exactly. The nuclear forces show saturation properties, that is, each nucleon interact with its immediate neighbors only, rather than with all the other nucleons in the nucleus. Now, nuclear forces are less than 10 Fermi. Non-central forces. So nuclear forces are non-central forces. This shows that the distribution of nucleon in a nucleus is not spherically symmetric, and nuclear forces are dependent on spin or angular momentum of nucleons. Forces between nucleons having parallel spin is greater than the force between nucleons having anti-parallel spins. Now, nature of nuclear forces. A Japanese physicist, Yukawa, postulated in the year 1936 that nuclear forces between nucleons arise on account of continuous exchange of particles called mesons between the nucleons. So later on, these particles were detected experimentally. They were found to have a mass about 270 times the mass of an electron. Three types of mesons were detected. Mesons carrying no charge were called neutral pi mesons. Mesons carrying unit positive charge each were called positive pi mesons. And mesons carrying unit negative charge each were called negative pi mesons. Now, according to meson theory or Yukawa theory of nuclear forces, all nucleons consist of identical cores surrounded by a pulsating cloud of pi mesons. Now, mesons or pions may be neutral or carry either charge, that is pi positive or pi negative. The difference between a proton and a neutron is essentially in the composition of their respective meson clouds. The force between neutron and proton is due to exchange of charged mesons between them. That is p positive plus pi negative mesons जो था. सो ये जो पायॉन्स में भी न्यूट्रल और कैरी चार्जेस जो हम लोग कह रहे थे पाई mesons जो थे पॉजिटिव और नेगेटिव वाले. Now, thus, proton and neutron continuously exchange their nature by absorbing and emitting pi mesons. Thus, ये पाई mesons वाला जो है ना, ये युकावा थ्योरी ये सब कोर्स में है नहीं, हट गया है, इसको हटा देते हैं, लोग बेकार में कंफ्यूज करोगे. I'll just remove this. Yeah, nuclear stability. So atomic nucleus consists of closely packed collections of protons and neutrons. The very large repulsive electric forces between protons uh, should cause the nucleus to fly apart. Nucleons are able to stay together despite the repulsive electric forces between the protons because of a much stronger force called the nuclear force. It is the attractive force that acts between all nucleons in the nucleus, and this force is much stronger than the Coulomb repulsive force between protons. The stability of a nucleus is determined by a value of its binding energy per nucleon. Higher the binding energy per nucleon, more stable is the nucleus. The stability of a nucleus is also determined by its neutron to proton ratio. A plot of neutron number n and a proton number, that is atomic number z, for stable nuclides is shown in the figure. The solid line in the plot shows the location of a nuclei that have an equal number of protons and neutrons. ठीक है, n is equal to z पे ये solid line है और ये stability को show कर रहा है ये जो dash वाले line है. ठीक है, note that only light nuclei are on this line, that is light nuclei are stable only if they contain about the same number of proton and neutron. Heavy nucleus on the other hand, तो तुम देखो ये जो स्टेबिलिटी है तुमको जो जो स्टेबिलिटी वाला लाइन है वो यहाँ पे यहाँ तक ही इसके पास है, उसके बाद फिर ये इधर मुड़ गया, राइट. तो लाइट न्यूक्लियाई में फॉर लाइट न्यूक्लियाई n is equal to z स्टेबिलिटी के लिए चाहिए. So note that only light nuclei are on this line, that is light nuclei are stable only if they contain about the same number of proton and neutron. Heavy nuclei on the other hand are stable only when they have more neutrons than protons. ठीक है, they have more neutrons than proton. Thus, heavy nuclei are neutron rich compared to light nuclei. This is as if neutron helps to stabilize the nucleus. तो जब stability देखो इधर गया, मतलब n का वैल्यू z से ज्यादा चाहिए, right? The stability of a nuclide is also determined by consideration whether it contains an even or odd number of protons and neutrons. So this is how you get to know about the nuclear stability. क्लियर है बच्चों? तो न्यूक्लियस में इतना ही करना है हम लोगों को. इसके बाद हम लोग अगली क्लास में रेडियो एक्टिविटी करेंगे. तो ये जितना थ्योरी पार्ट है इसको आप लोग पढ़ सकते हैं. So I'll upload it. Next class we'll start radioactivity basically. ठीक है बच्चों?
Yes, sir.
ठीक. Okay, so we'll stop here.